great to be here, and hello to the people watching online. I'm going to present two projects on behalf of a lot of people from my group, but also contributing colleagues from many different institutions. And I brought two different scientific software projects. One is Helios++, a LiDAR simulator, which is already well developed. And the other one is pytreedb, which is an object-based database for tree objects, which is in development and presented here for the first time to the public. Why am I presenting scientific software? Because I really believe that scientific software can be a perfect link between basic research and application. It can somehow transform complex knowledge to practice, and that's what we have also experienced the last years developing those projects. But what is Helios++? What is virtual laser scanning about? We call it a scientific method for remote sensing complementing the real data acquisition. It delivers as the real sensors point clouds and waveforms, and everything is done in a computer simulation. Why should we do this? You would argue, oh no, I have so much data, I don't need more simulated data. But there are several really good reasons why it makes sense to run simulations additionally. Because, yeah, it is low cost. You don't have to own a sensor, and you can still do LiDAR scanning. You can use it in education, even if you don't own your own LiDAR system. You can investigate all the options that you can set for an acquisition, like settings of the sensor system, even the sensor system, you can replace it, the trajectory, and so on. So Markus already presented a really comprehensive benchmark data set, but still there are many, many options that can be changed or done differently. As mentioned with the VUX1, you can just change one setting and the point cloud will look completely differently. And it's also important for generating reference data, perfectly annotated reference data for machine learning, and in particular deep learning, where you need so much training data because our trees are unique and no tree looks the same. So here we have a high demand for training data. And how is this implemented in our simulator, the Helios++? It's a C++ software. You can use it via many channels, or I would say, yeah, channels. You can run it from command line. You can run it from a Python script, from Jupyter notebooks. And we've even developed a QGIS plugin from where you can start it. And also the TU Wien has already implemented it into the well-known Opals software from where you can use it. It's completely open source. It's double licensed. This means you can also combine it with proprietary software. There is no limits there. And on the right side, you can already see a visual concept of the software. What do you need for a LiDAR simulation? You need a scene that you want to scan. This is like the 3D picture of the reality that you want to scan. You need to define your sensor, VUX1, a mini VUX or whatever. You need to define your platform. Is it an airplane or a drone? And of course, you have to define the survey. How should this drone carrying this scanner with these settings capture the scene that you have defined? So in principle, it's actually the same as in reality, but just done in a computer environment. And this computer simulation with Helios++ has a cool strength because it's modular. It's once you have defined the scene and you have your annotated scene object, you can just simply switch parameters and change parameters. And here you can see 4 versions of point clouds from the same scene, but they have been captured with different platforms and scanners. And of course, you can already recognize the strengths and weaknesses of the single sensors, like the occlusion effects of TLS that are coming out here in the annotated point clouds that are delivered from the simulation. We are already also thinking of how can we combine simulation and real data in a good way. And here we made an experiment of a small forest plot in Heidelberg with sequoia trees. Yeah, we have big sequoia trees in Heidelberg as well. And here the idea was, can we use real TLS data captured in the field to simulate ULS data using this real TLS data? And then we made exactly the same ULS flight and compared the simulation ULS and the real ULS data that we captured in the field. And in blue, you can see the simulated data, and in orange, the real ULS data. And in areas where we had good TLS coverage, it fits very well, and it resembles how a ULS point cloud should look like. But of course, we have problems where we miss the TLS data. I mean, that's clear. Now an example from our user community, from colleagues using the software, and those were Dee, Eto is also sitting here, and Eric, and they have developed a really cool algorithm, I have to admit, and also a tool for it. It's called Plant Move, and the idea is to have scans from plants that are moving over time, and you can derive the displacement of the plant by just using these 4D point clouds. And they used Helios to compare, to derive an accuracy assessment of their algorithm, because you can imagine it's extremely difficult to derive, if I'm allowed to say, ground truth for a moving plant. You would need another sensor, which is even better than the LiDAR, to get here reference or other values. And in the simulation, you can just move your plant in the scene, simulate it again, and then you have then you already know the displacement because you introduce it into the scene, and then you can compare the derived displacement from your algorithm with the reference displacements, and you can evaluate and find strengths or weaknesses of your algorithm by just simply using the simulated data. Now, making a soft cut, I would say, I switched to pytreedb, the tree database. It's an object-based library, so it's not a relational database with prefixed tables and so on. So you can simply add features to the object, and it's implemented in Python and MongoDB. But as you can see here on the right side, it has different interfaces how you can use this library. You can, for example, query and find the trees that you want to have by using a Python script directly, or you can use a well-defined REST API, so you're formulating a URL, an HTTP request to get the data that you want to have, or you can use a web portal to search and download trees that you are looking for. And the cool thing is, by using MongoDB in the background, you can scale it for really huge data sets, because you can just run it on the cloud and scale it to really big, maybe even a global database of trees. It's also completely open source. But now, going a little bit deeper, how do I define a tree for importing into the database? We decided to use the GeoJSON format. It's a very well-defined standardized format. You simply construct the geo feature in GeoJSON, having all the metadata and references to point clouds, URLs in your GeoJSON, and then you can just import this tree with all the measurements, field inventory measurements, species information, different point clouds into the database and make it searchable for your script or for the web platform. So for each tree, we have such a GeoJSON format that you can also open with GIS programs or R and so on, because it's a well-defined format. And then if you have your data prepared as GeoJSONs, you can just, this is Python code, you can just simply create your object here in Python. You define where do I have my zip file with all the GeoJSONs, here maybe on GitHub or some other cloud drive, and then you can just simply import all the trees into the database, and then you can directly start working with it. via Python, via the REST API, or make it available in the web portal at the same time. And here, this would be one query using Python code. I would like to have all trees which have property species RBS alba, and then you get all the results back as a variable, as a list, and you can just iterate over all the data that you got. But we have also created an example script for R, how you can use the REST API to query the database, because not all of you are working with Python. And yeah, we just made a first draft example function. Jannika Schäfer made it. And it's simply creating a post request, sends all the query information to the database server, parses the JSONs that come back or are returned, and then you can just simply download all the referenced LAS point clouds for each tree to your local drive, process it, use it as training data, and so on. Here one visual of the web portal, the third option to access the data. Here you can just create and formulate the filters with such drop-down menus. You can combine filters with logical operators. Here we would search for RBS alba trees which have ALS data available and ULS, or ULS data. And all those trees that we want to have should also have forest inventory data attached. Then we can preview the query. We can store a permalink to this query if you want to forward this query to other people or store it for your workflows. And then you can watch the result. On a map, you can watch the single tree JSONs and all the informations and all the referenced point clouds in the database. Yeah, now to wrap up this very short overview, we've seen the LiDAR simulator, which is already very mature, used in many papers by colleagues. We already have version 1.1. It is not a solution for everything, but it is fit for purpose for many things. It can complement real data, and in particular, if you need a lot of data, if you need a lot of permutations of your data, in particular for deep learning, it will be a very valuable tool. And the pytreedb, yeah, it's a very lightweight database which offers interesting interfaces, in particular to create automatic workflows. So if you have your forest growth simulator and you would like to put some point clouds in your scene, then you can simply search for the most fitting tree in the database and put the point cloud of this tree, leave on or leave off, whatever you need, into your virtual forest, into your digital twin, for example. And the two things also belong together. Like, for example, you can use pytreedb to construct scenes for Helios, just automatically create a 3D scenes by using the trees stored in the database. And the other way around, you can put simulated trees, simulated point clouds also in pytreedb to augment the real point clouds of real trees standing somewhere in the forest. So thanks very much for your time, and I'm very looking forward to the discussions the next days here in the workshop. Thanks.
Thank you. Thank you for that presentation. It was quite interesting to see this pytreedb. Is it an L or a B?
It's a B.
It's a B.
Base.
Database. Are there any questions from the audience? I see Kim is raising a hand.
I have a question about LiDAR simulations. When we try to simulate LiDAR data with, for example, Librat, which is another tool, we found our data was too perfect. And if we then use it to develop deep learning algorithms, it doesn't then work when we apply it to real data because we cannot simulate the noise of a real sensor very well. So what's your experience with getting the right level of noise, realistic noise, into your simulations?
Yeah, that's a really good point, and it's ongoing research. We got a new research project also working on this, and yeah, it's the matter of how can we fill the so-called reality gap and my hypothesis is that it's not really the best way to make the simulation or improve the errors or introduce errors into the simulation, but to combine real training data and simulated training data on different levels. Because if you think of deep learning, the basic features, you can also learn with simulated data, even if they are perfect. I mean, a building will look differently as a tree, also in simulated data. But if it goes to tree species or components of a tree, then you have to use real data to complement this in your deep learning approach. And I would say this could be the better solution than tweaking the simulation.
Well, thank you very much.